Gnanam paramam dheyam. Knowledge is supreme.
We need to find how these ladder operators, A operator and A dagger, how they act on eigenstates of the number operator. That's the first thing we will do as a curiosity test. Let's do that. So to do that, we may need to know the commutators between the number operator and the ladder operators. Let's first do this commutators. Number operator with A operator is A dagger A, comma A. Now on, I will not use a hat. Assumption is now we are doing from the rest of these lectures, it's all only operators. So I'm not really going to use a hat, but you will assume that these are all operators. Okay. So what will this be? A dagger with A. Which side the other A should go? This side. Very important. Why? Order matters. A and A dagger don't commute. What will this be? A with A dagger was 1. A dagger with A is -1, so you have a minus A. So commutator of a number operator with A operator is minus A. Suppose I operate it on a lambda state, which is an eigenstate of the number operator, can do this. What will this be? Na on lambda minus an on lambda, left hand side, equal to minus a on lambda. What is n on lambda? Lambda times lambda. It's an eigenstate of the n operator. So we will write lambda a on lambda plus n on a of lambda equal to minus a of lambda. Take this term to the right hand side and keep a of lambda to be some new state. What do you get? What will you get? Take this term to the side, so you will get n a of lambda to be lambda minus 1 a of lambda. So this could be a new state, but the new state is again an eigenstate of the number operator with eigenvalue lambda minus 1. What does that tell you? What can you infer from here? I should be able to write a of lambda to be some coefficient times lambda minus 1. If I write a of lambda to reduce the state to lambda minus 1, then the number operator on that state will pull out the eigenvalue as lambda minus 1. You all agree? What else is possible? Anything else possible? This is the only possibility. Looking at this, you can say. Okay, so this is one thing which we infer from that equation, which is also equivalent to n with a is minus a. From this we derived. So can you redo the same thing For n with a dagger, what it is? It's plus a dagger, and then operate it on the state lambda on both sides and write n operator on a dagger lambda to be lambda plus 1 times a dagger on lambda. Okay. What will this imply? This will imply a dagger on lambda should be some d lambda times lambda. Something wrong. Lambda plus 1. So clearly, it is not an eigenstate of A, it is not an eigenstate of A dagger, which is expected because the commutator is non-zero. It can't share the same simultaneous eigenstates of hat n operator because the commutator of n with A is non-zero, commutator of n with A dagger is non-zero. But after we got this, you can also see whether A dagger A operating on a state lambda gives you the state back to lambda. You can see that if you do A on lambda, it takes you to lambda minus 1. If you do A dagger here, it will take you back to lambda. So it is an eigenstate of lambda. Very consistent. So we are just playing around with operators, algebra. For the particle in a box, I'm not sure whether we can do this ladder operation, because first of all you have to write your Hamiltonian and see whether you can rewrite the Hamiltonian in terms of ladder operators. Okay, so in the particle in a box or the step potentials, you don't have this freedom because there was a quadratic potential here. This freedom of writing in terms of ladder operators happened. But there are many systems where you could do this. I'll try to tell you later. Like for example, if you want to write potential like a cosecant squared potential. Let's take cosecant squared x. Can you solve the solution if someone asks you? It's not very easy, but you can construct a cook up a ladder operator A and A dagger, but then that leads you to a separate quantum mechanics problem, which has been done. A lot of these potentials have been done introducing a cooked up ladder operators. So this part is not, generally this ladder operator way of doing it is invoked in many complicated systems. Here it turns out that both were quadratic and you could do it neatly. There we will start introducing some W and then we try to construct an A dagger. There is a systematic way of doing it and it's very powerful to get an operator method of solving the system. In fact, you should see one article in Resonance. I think it's 2003 or 2004 where I've written an article with one of the seminar students on supersymmetry, where we have reviewed basically that a particle in a box can be mapped to a cosecant squared potential using this ladder operators in supersymmetric context. It's very nice. It's just quantum mechanics problem, but you can get all the wave functions without solving the cosecant squared potential, but using this ladder operator. Take a look at it if you are interested. Okay. So you can search for my name in Resonance in Indian Academy. 2003, 2004 is my memory. Yeah. Now you can see why it is called ladder operators. What is happening? This is what is taking you down from lambda to lambda minus 1 by one step down. This one raises it by one step. Still lambda is non-negative real. Okay. But by doing this, you can keep doing A many times. and you cannot cross 0. You cannot get negative pieces, right? You all agree. So if you want to go in steps of 1, you have to at most hit a 0. What is the possibility? Suppose lambda was 1.5 or something. If I do first A, it goes to 0.5. If I do another A, it will go to minus 0.5. But minus 0.5 is not allowed because your expectation value of the number operator can be greater than or equal to 0. So lambda has to be necessarily an integer. If suppose lambda was 5, I can go to 4, I can go to 3, I can at most reach the 0. After I reach 0, I would claim that these coefficients are 0. Okay. So it's basically working out the logic whether we can try to argue lambda, even though it is real and non-negative, can you have it to have some decimal points and not violating what you need for the matrix elements or expectation values of the number operator. Okay. So just think over it. That's the ladder operation, and finally where you can hit. Okay. Just kindling you to think about it. Okay. So just to check out these commutators which we have already done now. Okay. And then using that commutator you can show A on lambda is an eigenstate of hat and operator with eigenvalue lambda minus 1. Everybody is with me? And sorry, this has to be A dagger. A dagger on lambda is an eigenstate of again the number operator with eigenvalue lambda plus 1. There are a couple of things which you should keep in mind. These eigenstates are all normalized. These are eigenstates of the number operator. So we will have them to be normalized. Okay. So there should be a subscript lambda that is missing here. A on lambda is C lambda times lambda minus 1. A dagger on lambda is D lambda times lambda plus 1. So can you determine C lambda and D lambda using this above data? So can we work it out? Can you use this data and determine what is C lambda and what is D lambda? You have A on lambda is C lambda times lambda minus 1. So you can also write C lambda squared lambda minus 1. What is this left hand side? What is left hand side? Left hand side is lambda times, it's an eigenstate of the number operator with eigenvalue lambda, which is C lambda squared lambda minus 1 lambda minus 1. So this implies C lambda up to some phase factors is square root of lambda. So what have we said? We got A on lambda is square root of lambda times lambda minus 1. If lambda is 0, you get A lambda A0 has to be 0, which means you don't go below lambda equal to 0. Do the same thing for d lambda. What is this? Yeah, you can try to use the commutator and write it in terms of this can be written as n operator plus 1, right? Is that right? Using the commutator. If you use a dagger to be 1, implies a dagger is 1 plus a dagger a, which is 1 plus number operator. Okay. So this will give you lambda plus 1. Okay. So you will get lambda plus 1 to be d lambda squared. So that tells you clear? Can now check a dagger or a dagger a on lambda is lambda times lambda, whether that is also happening. You can see that that will also happen. You can check that out. You agree? Because on the lambda minus 1 state, if a dagger operates, it will give you square root lambda times, it raises it back, so you get, which is consistent. Get back this. Am I right? A on lambda is root lambda times lambda minus 1. A dagger on lambda minus 1 will be again root lambda times lambda. It raises it by 1 unit, and you have that the number operator is an eigenstate with eigenvalue lambda. Everything is consistent. Okay. So if you draw the lines, you have lambda minus 1, you have lambda plus 1, lambda plus 2, and so on. So you can have lambda minus 1 and you can go below. This one is done by the a dagger operator. What about this one? It's an a operator. You can do first a dagger and then an a. It will get back to the same state, and so on. You can play around even pictorially and show that this is a beautiful ladder operator. So what is the summary of what we have done today? First, we introduced from X and P in the harmonic oscillator. We went on to A and A dagger, and using this algebra of X and P equal to IH cross, we went on to write A dagger commutator is 1. Then we used that we can write our Hamiltonian as n operator plus half times h cross omega, where n operator is nothing but a dagger a plus half times h cross omega. Then we said Let's take the eigenstates of the number operator, which are eigenstates of with eigenvalue lambda, and we also use n with a to be minus a to imply a on lambda as square root lambda times lambda, lambda minus 1, which is the lowering operator in steps of 1 unit. And we also had n hat with a dagger to be plus a dagger, which implies a dagger on lambda to be a raising operator with a separate coefficient, different coefficient. So using all these information, if we keep going, we have to make sure that any state which I write, a state chi with the number operator, some state chi, I need this to be always greater than or equal to 0. This will force your lambda cannot become negative, cannot most become 0, and to go to the 0 state, I need to use these ladder operators, which goes in only in steps of 1. It is not going in steps of fractions, right? So you have only in steps of 1. You can go from, say, let's say lambda to lambda minus 1 with an a operator, and you can again use an a operator, go to lambda minus 2, but at most you have to hit a value such that the number operator on that state, let me call it as a ground state, on the ground state can be the lowest value has to be 0. You can't go below that, because your state has to satisfy on any state, n operator on any state has to be greater than or equal to 0. This forces you that you cannot go below the lowest state. Okay, and this is possible. If you go through these, it's possible to reach a state which is 0, lambda will be 0 times 0, only if this is an integer, positive integer. Otherwise you cannot achieve this. Formally, for any quantum system, it has to be real non-negative. That is all you have. But now with this construction, you see that you cannot have it to be any other, real values. It has to be only integers. Okay. So therefore, so lambda is an integer which we will denote it by some n, and write our states as n hat on n is n times n, and Hamiltonian on n is n plus half times h cross omega on n. So did we really struggle to get this eigenvalue? We went through the operator algebra. We did not solve any differential equations, but we ended up getting the familiar eigenvalues of your harmonic oscillator beautifully. Okay. How do you find the wave functions? How will you find the wave functions? Tell me your harmonic oscillator wave functions. You can take a x with n. What about a on 0? Let's write what is a on n before we write this. A on n is square root n on n minus 1. So a on 0 will be A operator is X with up to a constant which is dimensionless plus IP, right? A operator is X divided by some something. A position representation of A operator will be okay. So what we will do is we will take A on 0 and take a position state. A on 0 is 0 and let's simplify this. So X on X is X, right? You can put an X naught if you want and you can write X naught with X operator will be X naught X. A was P plus Ix. Did I wrote P plus Ix? Sorry, if I have done it, I am wrong. So what is the differential equation you will get out of this? So you will have an X naught divided by this and there will be a del by del X which will be del by del X naught on the state, right? So what is that equation? Alright. What is this piece? X naught with 0. I have said that X with any n, I am going to call this as psi n of X. So X0 with 0 will be psi 0 of X. And I want this to be A on 0 is 0. A on 0 is 0. So use that. So this will be equal to 0. So it is essentially a first order differential equation psi of X0 with X naught up to those factors. What are those factors? 2h cross, let me cancel. So you will have a h cross by m omega, I think. Can you solve this equation? This is 0. And are you getting your familiar ground state wave function? Please check it. So I am just showing you, I didn't do much, I just used the ladder operators. I extracted for you the eigenvalues. Now I am also saying you can familiar position space wave functions can also be derived. At least let us derive the ground state wave function. Once you have the ground state wave function, you can go to the next one. How do you go to the next one? You will have A squared, A dagger operating on that will give you the first excited state and so on. So we can systematically go finding the solutions for the harmonic oscillator once you understand the power of the ladder operation. There are some curious questions I want to ask you. Can you find the eigenstates of the A operator and A dagger operator? Try it out. Find the eigenstates of A operator. It will not have real eigenvalues. Why? It is not Hermitian. But can you find the eigenstates of A operator and A dagger operator? That's a question for you. Think about it.